Um, there will be more people coming in because we got a line downstairs. The Wi-Fi, I was told, is about to come back on. AT&T has finally done their wire, and they're booting all the routers and stuff up right now. So hopefully in the next 30 minutes we should have Wi-Fi, and the Wi-Fi, we will post it as to what it is. If you'll notice on the side here, we have tables with chargers. So if you're doing a laptop and you come into a break, then this room will be closed, so you can leave your laptops charging so that you can make notes or minutes. But we also gave you tablets. And the big thing, and Paul is going to jump all over me about this, is the scoring sheets. Those are important for the success of the technical papers, because at the end we will make a decision, not only from the reviewers that reviewed all these papers, but also from you as the audience, as which one is the first, second, and third. And there is a monetary reward for that. So it's important. So please turn in those papers daily. You will get one tomorrow. That paper is good for all day today, correct, Paul? Okay. From a safety moment, I don't have a Hilton person here, but if we were told that there is no alarms or testing that was supposed to take place. So if we hear alarm, there's stairs there in the back of this. If you go out the side here, there's stairs there, and there's the escalators if they're still working, and you can go to the parking lot of the Hilton by the pool. That'll be our assembly area. All you end users, you know exactly what I'm talking about. So I'm going to turn this over. Del Merriman is another chair. We're kind of the organizers. And Stuart is also a chair. So I'm going to turn this over to Stuart. He's going to do the opening presentation.
I'm going to use this, I think. Okay. Can everybody hear me okay with this? Sounds good at the back? All right, thank you. Thank you and welcome. Yeah, my name's Stuart Simmons. Despite the accent, I'm from Canada. And I'm esteemed to be with Wes and Dale for the opening remarks. These guys have done it many, many years, of course. It runs very seamlessly, and now they just want to hand it over. So welcome, and welcome to everybody that's new. I bumped into 2 or 3 people on the way up the escalator this morning that are new to the event, which is fantastic. So for many of you, of course, you know we've been running this since about 1955. 1 or 2 people in the audience have been here since 1955. But of course, we've changed the name, and we'll explain that as we go along today, exactly what it is. But this is the 2nd annual ATC event, and we'll talk about it as we go along. Just a quick bit of information on the bits that Wes didn't fill in on. Here's your hall, upstairs and downstairs in the pictures. We're upstairs this year. For those of you who haven't been here before, you'll know this is new. We've tried to change the event slightly this year, give you a little bit more room, hopefully sound a little bit better, have a bit more sight line. So hopefully that's good for everybody. Downstairs in the hall, again, if you've been here before, we used to take half the hall. Now we take all the hall. So there's a bit more space to roam, a little bit more space to sit around, have those private meetings and chats at the same time. And the entrance, as you know, is where it is. Everybody's happy there. A little bit about the new look, the little bit new format for the place. We've changed the dates. Thankfully, everybody got it correct. I did meet an old friend yesterday who thought it was Sunday, which is wonderful. We used to be Sunday to Thursday and drag everybody in on a Saturday or a Sunday. We decided that was not valid anymore or necessary. So this is our format, Monday to Friday, and we will do this going forward. Monday is our technical training day. For those that were there yesterday, we had a fantastic turnout. We had about 120 students yesterday come through the halls, or techs and so on, come through both of our tracts. We do a fundamentals course, which runs through the basic understandings of all analytical instrumentation in a program throughout the day. And we do an advanced course this year, was focused on sample handling systems. We do a common one on that. We've expanded our show back now to... We can't hear you. You can't hear me? Can you hear me now, Rocky? It's my English accent. What we do is we mumble, and then we hand you a flag, and you're in the British Empire, buddy. That's how it works. Suddenly we own you, and you didn't realize it at all. That's the rules. We've been doing it for years. We're quite good at it, apparently, you know. Yeah. How about that, Rocky? You hear me okay now? Yeah. All right. Okay. So yes, we are now, Tuesday, Wednesday, Thursday will be our event, of course, starting today, all day tomorrow. Papers in this hall. All the rest of the event will be down in the vendors hall, including, except for the breakfast, which will be up here. Everything else will be down there. All the drinks, all the sponsors and so on will be downstairs. Technical papers in here. The vendors hall is expanded. And we work very, very hard to maintain the high quality of the papers. It's paramount to the origins of this conference. It started out once without any vendors hall, and it was all about papers. And now we thankfully have that hall. Everybody loves it. Both the people visiting and the vendors, of course, love the hall, and we love that time. But papers is paramount. We really hope you enjoy the 24 that we have for you this year. We had extras. It's always wonderful to have spares. We'll talk a little bit about that as we go along.
I'm going to keep you on time here.
What time do you need me to be? 8:30, I think, right? For those that are here first time, we're very, very happy to have you. Thank you so much for coming. I see a lot of familiar faces, but I've met one or two new ones, which is wonderful. We're very happy to have you. You get a wonderful mix of everybody in this hall and everybody that relates to analyzers. So as we've looked out at exhibitions before, we've been to many places around the world. Some of us have been all over the world doing exhibitions. You know that we tend to get lumped in with lots of other bits of instrumentation. The wonderful thing about this show, this event, is that it's just us analyzer folks. Quirky as we are, as weird and wonderful as we are, it's just us. So when you look around that hall and you go to every booth will be valid to what you do. Almost all of them will be valid to what you do. And that's a wonderful place to be. And we get a lot of end users. I believe our end user count is up this year, which is fantastic. So we should be good. Quick thank you to the volunteers. It takes quite an army of people to put this event on. It takes a lot of history to put this event on. Between Dale and Wes, who've been doing this many, many years, we are pretty good at what we do here, but it still takes a big army of people. I won't read through the list, but I'm sure a lot of them are familiar to the people that are here. But we're very grateful to those people. We're very thankful. And we are always looking for volunteers, should anybody wish to sign up. So please come find somebody. We're not all as young as we used to be, and we're definitely looking for some succession planning eventually along the line. So please come find us. Here's your conference agenda. Yesterday was training. We described that. Big thank you to the 6 or 7 people that did that. Phil Harris did the advanced. The rest of the team there you see on the board, esteemed people in the industry, except myself, of course, doing the fundamentals training. 3 days of papers. We split them up a little bit this year. We used to jam in 3 in every little session, but now we spaced them out. Paul Barnard at the back looks after all of that for us. They'll all be in here. And then Friday's hands-on training. I've listed the companies that are there doing hands-on. So this is primarily for the techs, but anybody that wants to get themselves inside any of the analyzers. They all put on their individual events. We give them a room downstairs. They bring their own material. It's usually about 4 hours in the morning. And please sign up. We have a number of people already signed up. It's open right until the very last minute. You can come in on the day if you decide you want to see one of those guys. They are all in the vendors hall. So if you want to go and discuss what their training is about, they're certainly there. Please go see them. Breakfast, everybody is. Oh. These are them, if you haven't seen them. But they are in the program, should anybody want the program. There are QR codes down the front if you want to print it onto your phones. And it's also on the website if you want to go to the ATC website. Breakfast, everybody's found, I hope. Breakout sessions will be downstairs in the vendors hall. We currently have, and it does change very quickly, we have about 74 vendors, about 85 booth spaces. So that's bigger than we've ever had it before. That's fantastic. We do have a spouses program, should anybody have their spouse with them and want to go out and about. There's a program for that, so come see us or come see Dale and Wes. They'll fill you in on that. We have a technical paper award that Wes has already described, and we have a product of the year award that we will do too. We've added this year a little bit into the hall. We're looking to expand a little bit. We are very oil and gas focused. Of course, we're in the Gulf Coast. We're trying to see if we can add a few more tracks to what we do, see if we can expand ourselves. We've offered up a booth this year to the GPA midstream pipeline companies. Please go see them. Please go talk to them. There's some very interesting stuff that they're doing, and we're very interested in bringing a few more people into the event. We've got over 100 students attending today who are very excited and interested to come and see what the industry's about and to come join our team as hopefully as possible. And we have a resources booth. Should anybody be looking for people, please go to the resources booth. You can put your name down there, put down what you're interested in, direct people to your vendors hall booth if you're interested in that. Wes mentioned this already, but this is a very important part of what we do. It's validation for the effort that the people's put in with their papers. They've been marked by a team run by Bakvu of Chevron over the last month, 2 months, 3 months back. And they are moderated and looked after by Paul Barnard at the back. So they've been scored already for their technical content as read by the invigilators of those papers. But we ask all of the audience to do their part. And we've handed out those papers today. We usually hand them out every day. If you don't have one, Paul is generally at the back of the hall, the esteemed gentleman at the back, also Brit. So we take over from front and back. You can't hide from us. Paul will give you another paper should anybody need to have one. And the idea is, how is the presentation done? So they've done their paper. They spent a lot of time on that paper. Now they've spent a lot of time on their presentations. How was the presentation? Does it have technical value to what you do? Do you see where it's going to go in the industry? Please mark them up and hand them to the back. That helps us score. It also helps them validate the effort that they put in. We have a secret, very secret team. It used to be run by Wes, so it wasn't secret at all because everybody knew Wes. And he'd come around your booth and you knew you were in for the product of the award. But this year we have a secret team. If you want your product in, please go to the front and just let them know that you would like to be considered for product of the year. And then that'll go into the pile. And at some stage during the show, they'll come around and look at your product and it'll get evaluated, and then we'll release that award towards the end of the year, end of the week.
And that team is made up of nothing but end users?
End users only on that team, no vendors involved. There is the Wi-Fi. We have things for it down at the front too, should you need to find it. I think it should be up and running soon. It wasn't running yesterday, but I think it should be up today.
Wi-Fi is working.
Wi-Fi is up. Everybody go, and then it'll be down in a second. Spouses program, should you need it, come find us if you want to find out where the spouses program is. We'll fix that up.
Some people coming in to go to this side of the room. Go back on this side.
Everybody got it? Plenty of room at the other end of the hall for anyone that's coming in.
Yeah, we're real heavy on this side, and we're real light on this side. So if you're tired of sitting beside whoever you're sitting beside and want to move over here, there's lots of room over on this side. We're heavy, heavy, heavy this side.
We're listing. That's okay.
Yeah. We're teetering this way.
Did you get it, Marco? You good? We have printouts at the front too, should you want one. It's 8 numbers there, Marco. Come on. All right. Okay, ground rules, of course, are always the same ground rules. I'll get it for you. Did you get it? Ground rules are the same as always. Please be respectful. The guys spend an awful lot of time getting their papers done. And then an awful lot of time getting their presentations done. And it's a little unnerving, of course, for anyone that hasn't been up here many times. It's a lot of new faces that come up to present. So please be respectful, be there here on time, be as quiet as you can. Slip in quietly if you come in a little bit later, or slip in the back doors if you need to. Our papers are heavily watched for too much commercialism. We want them to be technical. We want people to find merit in what's out there. So hopefully you find good value in what they do. And we usually, and it's been a little bit better this year because we've allowed a bit more time for it, questions at the end. Please give them questions. It's wonderful feedback for them. So if you've got any questions, we'll usually find at least 5 minutes at the end of every presentation to give them that. We hope you have a fabulous week. We really do. We look forward to any feedback that you have. It's an evolving thing, and we'll describe a little bit about where ATC came from in a minute. but it's important to us that we give the event what everybody wants. We're very conscious that this is an opportunity for all of our industry to enjoy what we do. So any feedback is welcome. Anything you want to tell us, we're very happily receive it. Thank you to everybody. Before we hand over, I just want to give you 5 minutes on the explanation between ISA-AD, the Analysis Division, and ATC. There is some complication and it's quite confusing, but of course this event from 1955 onwards was part of the ISA Analysis Division. It's the original division in ISA and we're very, very proud of it. There are papers running back to almost that time, which we are trying to get into everybody's hands. We were once, if you were at an event about 10 years ago here, everybody got a handout with all of those papers on it. And we're going to try and build that up again. We have a lot of them online now at ISA, but should anybody want them, it's a wonderful place to be. During the COVID period, of course, nobody was live eventing anymore, and we took a break. Everybody took a break. But we polled our community at the end of that period, and it was overwhelming that everybody wanted to come back. ISA decided that for now, they are not doing many live events. So we took a decision then to host this event last year. ATC 2022 was the first one that was done. Since that time, we are in discussions with ISA about what that means and where it belongs to them. But currently, to be clear, it is an independent organization. ATC is entirely independent from ISA, and they would like us to remind everybody of that. What it means for all of us is something slightly different. I'm sure a vast majority of you out here are ISA members, and I would welcome that. I was up until last year the director of ISA Analysis Division in my 2-year period. It was supposed to be handed over this year to Paul Camerata of Dow. Unfortunately, Paul left the industry about 2 or 3 months ago, and we're scrambling a little bit. So I've stepped back in to keep it together for now and to decide what we're going to do for it. So I'm currently the acting director of ISA Analysis Division until such time as we decide the way forward. But this event now is independent of those guys, for now. So we want to be clear about that. So now that we're not doing that event, what is it doing? Well, the membership of ISA-AD is about 1,300 people, and we manage that online these days. Has a long history, and it's part of a AT division within ISA. You can easily join a division, should you not be in the analysis division now, but are a member of ISA. All you need to do is click the box. You can click more than one box as it happens. You can be more than one division member these days. They used to limit you to 2. Now you can have as many as you like. But if you are on ISA, I would ask you to go click our box and be a part of the analysis division. We do still exist. And as I say, we are building that library within our webpage. They changed during COVID to put everything into a system called ISA Connect. And ISA Connect is a portion of their... All right, here we go. ISA is a portion of the website, ISA Connect. And that's where all activities are done now. So all of the events, so now that we're not doing an event, everything that relates to everything to do with ISA Analysis Division is within that Connect system. So if you want to know what's happening, you have to be a member of Connect. Now, it's not a perfect system. It's a version of LinkedIn, for example, and you need to actively join it. So even if you are an ISA member now and an Analysis Division member now, you still need to build your own account in ISA Connect, and we would ask you to do that if possible. That would be great if you could do that if possible, and then at least we can contact you and talk to you and show you what we're going to try and do. These are the general chairs of the Analysis Division, and we have to have a number of them, but there is some flexibility within that. As you can imagine, as we've rotated from ISA-AD as this event to ATC as this event, we are currently sitting with a bunch of volunteers that I'm happily keeping volunteering for both places. But at some stage, we would like to separate the two up. It's a lot of work putting on this event, and there's some work to go. It's going into Connect. So our intention now that the two places are somewhat separate, will be to try and find new volunteers that would be interested in doing some of these portions online. Connect, that's the front page, as you can see there on the slide. And it has some useful places. One of the best places it has is its library. And one of the things we've been missing, I think, over the years as this event is the ability to store our data and to add information, to build presentations, to give webinars. So there is absolute merit in running this thing in parallel with what we're doing here. We can put our papers in there, we can give technical papers in there, we can put our fundamental courses in there. So the library is very, very useful. And over the last few years, I've been adding some papers in and putting some ideas in there, but we would certainly like to expand that, and I think it could be useful for everybody in the long run. We could also do presentations online, some webinars. Everybody's doing those these days anyway. We could do a couple of those through ISA events too. There is a bit of structure to ISA these days, and we have a thing called being in good standing. It basically means we have to complete a number of events over the year, and we have to account for ourselves over the year, but it's really not too onerous. But we have a certain number of things to do, and we have to keep ourselves in good standing. We should ordinarily have a director and a director-elect and have those people lined up so we have succession planning continually moving within the process, and we would hope to get that going again relatively soon. If you look at this, this is the rough list that we gave everybody last year of the sort of things we'd like to do. The annual report is done, and the business reporting is done by the directors. That we have particular chairs that relate to online content. They have a particular interest in young people. There are lots of young faces out here, but there are a lot of older people out here doing the job for 30 plus years or so on. So we're always looking for young and exciting people to come into the industry. Have a few meetings, garner some ideas, be part of that ISA community. That's one of the things I want to do. We've been handing out scholarship awards for a number of years now, both independently as the ISA Houston section of what we do here, but also as ISA AD. We're a successful organization. This event is one of the most, if not the most, successful event that ISA ever put on, and we generate a little bit of income for them, and we've been giving that back as scholarship over the years. So there is a scholarship award, and that's a nice thing to do. Feels like a nice thing to be able to give back. We add to our content page, and we allow, should we need to, that area for people to talk to each other, a little bit like LinkedIn if you want to just chat, ask questions, get some feedback. We did a survey a couple of years ago just to see where we were at, and there were two very interesting things that came out of it, and I think that speaks to where we want to try and co-join these two events. Everybody wants to be here. That's absolutely paramount, and that was our return retort to ISA about whether we would go online or whether we would be live. It's very clear we want to be live. We were live last year, even when we were just releasing ourselves from COVID. We absolutely know it's the right thing to do. And judging by the numbers we have today already, we know we're on the right track. People want to be here. We want to be face-to-face. That's how our industry works, belly to belly, as an old friend of mine used to say. But the other thing that came out of that survey is that we are looking for places, repositories for information. There are quite literally thousands of years of knowledge sitting in this hall. And it'd be a wonderful place if we could find somewhere to keep that knowledge. We all keep it individually, we all have little spaces for it, we share it with one another, but perhaps if we had a proper repository, that would be a good place to do that. And strangely enough, ISA Connect is that place for us. We do have a place where we could put that together. On your right-hand side there, looking at it, those are some of the things we got back as feedback. God, it would be nice if we could have some place for the white papers, best practices, fundamental understandings of technology. So there are lots of good things there that we can put, and we need a little help to get there, of course. I got a nice response on people willing to volunteer. This event requires a reasonable amount of effort, and it obviously accelerates as you get closer to the date of yesterday. And not everybody can commit to that. We fully understand that. But the online content thing could be once every 3 months. Hey, I've got a good idea. Do you want me to write a paper or a little story, a little blog? Absolutely is always the answer to that. So perhaps anybody willing to volunteer or interested in volunteering but don't feel they can commit to the event like this one can certainly do something as part of ISA Connect, and we would welcome that. I highlighted in red at the bottom there the sort of new things that we're looking for because they differ from the volunteer team that we've always had in the past. So somebody that would look after the Connect program, somebody that might deal with live events, live chats, live meetings, content editors, and particularly the young persons people. So if any of that strikes a chord with anybody in the room, please come see us. and we'll help to get that going for you. We're always looking for volunteers, and you don't need to be an expert. Please don't be intimidated if it's your first day on the job and you feel like you have something to say. People that are willing and keen to help will be heavily supported by people that have been doing this a very long time. So please come forward if you want to do that. We like doers, and we'll help them out with a couple of experts here and there, so that would be fantastic. And strangely enough, we like young people that can understand computer programs and online blogging. That would be fantastic too. All right, so just to wrap up, the message from our community, from what was once the analysis division community that still exists, is that we want our symposia. That's 100% the very reason why we've created ATC. Even though it stands alone a little bit from ISA, we will continue to have this event. We will continue to grow this event. We might even continue to move this event around a little bit over the years. But certainly this is here to stay. It might be the second year, but we intend to get it as long as the original analysis division was running. So please don't be worried about symposias. That's the very reason why we've done what we've done. But there is room to be part of ATC and part of ISA to continue. As part of that long history of analysis division, it is the oldest division. We've run it for a very long time. We'd love to see it continue. So, and we feel that there is space to do online content, particularly in that library repository, for everything that we know and everything that we want to hear about. So I think we can run the two things in parallel. So that would be my pitch as the guy that stands as the liaison between ATC and AD. Please come and be a part of both of those things. We'd love you to be there. With that said, thank you so much. Welcome to ATC 2023. I hope you have a fabulous week. I hope you learn everything you need to know and find everything you need to find in the hall. And if you have any questions for any one of us, please come find us at the front or wandering around the halls. We're absolutely delighted to have you. Thank you so much.
I just want to reemphasize to everybody, ATC is a separate organization. Everybody you see on this stage, we wear two hats, right? He just had his AD hat on, and now I've got the ATC hat on. And that's how we have to do it for now, okay? There's reasons for that. If you want to know why, you can come see one of us, and we can discuss it. But it's a lot more to it than just, you want a face-to-face, we have to do ATC. Bottom line. You want a face-to-face, we have to do ATC. You want a virtual, we can do AD. You choose. You're the people that make that choice. And you've chosen. So, thank you for coming. Dale? No comment is normal. Paul, we're going to start with the technical papers. Thank you all for being here. This is very important.
Okay, now it is. Some presenters did not get their PowerPoints to me yet, so they're not loaded on the laptop. So if you're one of the guilty people, please come to us 15, 20 minutes before your session starts so we can get them loaded onto the machine here and meet your session moderator. Okay, thanks.
Then next, I want to explain our analyzer. It's called PLGA 1000 Process Gas Analyzer. Then next, I want to explain our new technology. It's called ARM, Infrared Laser Absorption Modulation. Then finally, I want to show you our results, and including a field trial in the ethylene plant. Okay, so this is our background for our development. So we are focused on the ethylene plant. As you know, ethylene is the largest feedstock for the petrochemical industry, then reaching more than 180 million tons in 2020. This production is by stream cracking or thermal decomposition of the ethane. So ethylene is starting chemical for many other products that need purity above 99.9599. Then ethylene is a byproduct produced during hydrocarbon cracking in ethylene product furnace. Ethylene contamination level is the ethylene product is in the range of 10 ppm or more lower. Then we are focusing mainly two applications. So this slide shows the one focusing application. It's a ethylene converter. So ethylene converter is ethylene hydrogenation is a highly acidic reaction. Careful control of the reaction temperature is critical to plant safety. Integrated reaction safety system is essential for the safe operation of the ethylene plant. Then our target measurement component is methane, ethane, ethylene, and CO. This is our specification, target specification for 4 components. So ethylene converter inlet outlet. Of course, outlet is very low sensitivity, low concentration measurement requirement, like a 10 ppm or less. Then our target specification for the performance, 1% of full scale for the linearity and repeatability. And the response time, 3 seconds TD plus and T90. And also calibration interval is 1 month. And the second key our application is a C2 splitter. Also, this application is important for the ethylene plant. The separation of the ethylene from the ethane by distillation is normally the final step in the production of ethylene. So that's why it's important for the impurity. Then this is also a target specification for the C2 splitter. So performance of the specification is the same as ethylene converter. That is our target. Okay. And next, from this slide, I want to explain our analyzer. It's called the PLGA 1000 Process Gas Analyzer. So we exhibited this actual product in our booth. So later, you can show the actual product, and then you can open the door, then you can show the actual key component as well. So this analyzer has many advantages in gas sensing. So high resolution mid-infrared laser system, and 3 seconds analysis time, and high sensitivity in minimum 20 ppb. And also this analyzer equips up to 6 lasers per application. It depends on the customer requirement, and robust, simple, and compact. And also, I later explain high sensitivity by unique interference collection method. That is one key component, keyword. Okay, this is a specification for the PLGA 1000. We are using QCL, quantum cascade laser, as a light source. And we have the hazardous area classification, class 1, DB2, ICEX, and ATX as well. And we have this analyzer has a 3-channel for the communication, Modbus TCP/IP, and digital output, analog output as well. And temperature specification, minus 10 degrees C to 45 degrees C. That is the specification. And next slide shows our analyzer picture. Right side showing the total picture, and the right bottom one is open the door inside of the analyzer. Then left side just focus on the optical unit. So this analyzer, this left slide, left drawing showing just 4 QCL laser configuration, up to 6, but this drawing showing just 4 laser. So we have 4 laser, then laser emits light to the lens and filter unit, then to helio cell. So helio cell, almost a 5 millimeter cell, then back to the detector. This is our simple QCL laser configurations. And this analyzer has two key components. The one is the QCL, quantum cascade laser. These components are made by Horibet Japan. Then the operating wavelengths can be selected by the designing the structure of the material. It means Horibet Japan manufacturing this laser by ourselves. That's why we can design the suitable to the customer requirement. And also, Horibet is capable of the manufacturing QCL wavelengths adjust approximately for each gas application. And this one also key component, multi-pass cell. It's helio cell. So this helio cell is 5 meter, with a cell volume only 40 cc, 40 milliliter. The small cell volume allows the gas to be replacement rapidly and increase analysis speed and response time. That is important. And in addition, the surface area of the cell is very, very small. And the risk of the adsorption can be reduced. The design is compact and suitable for field replacement. That means easy maintenance for the customer, for the service person, analyzer tech. Okay, from next slide, I want to explain our new technology, ARAM, infrared laser absorption modulation. It's a new technology. Then ARAM is a method for the data collection and analysis. So QCL are scanned with current to collect 500 data points per laser. And the spectral features are extracted from the sample spectra. And non-spectra are compared to sample spectra in a no database to determine concentration. Spectral interference, such as band broadening, temperature and pressure influence, are compensated by extracting the future quantity related to each disturbance. Calculation speed and accuracy are drastically improved. This slide is just general. So I'm using absorption method of IR. So each component has absorption wavelengths corresponding to band. The laser has high wavelength resolution. They can scan narrow area in the red square, in the dot blue square. So HORIBA can target sample absorption while designing to minimize spectral interference. RM has the advantage of the compensating for temperature, pressure, and spectral interference effect. I can show the interference and coexisting effect. So, for example, our target gas, ethylene, it's a blue one. Blue one is the target gas for the ethylene spectrum. But sample gas containing other gas, like ethane. So ethane spectrum is the orange one. So our target ethylene has an interference ethane. So that's why spectrum is overlap. It's called interference effect, like a red zone. It's an interference effect. And this ethane spectrum, its ethane concentration increased. That means ethane spectrum is moving up. Then our target gas, ethylene spectrum, the spectrum is changed. It's like a flutter. So that means spectrum broadening. So our technology need to care both interference and the coexisting effect, both. Then this slide just showing the comparison of the NDIR versus RM. The left figure is NDIR. Detector has that detect the amount of the absorption at the specific wavelengths and convert it to concentration. On the other hand, the RM in the right figure reads the signal from the detector in unit of the time and convert it to the concentration from the database. It's obtained in advance. So database already we obtained, we created a database in advance. And this slide showed our calculation method of the future quantity. So the future quantity can be obtained by sum of the product of the absorption signal and the future reference signal. If the shape are similar, the future value becomes larger. If the shape are not similar, the future value becomes smaller. Since this future quantity is proportional to the concentration, it can be quantified by assigning the value based on the concentration at the time of the future quantities acquired. So future reference method, the center line, red, blue, green, and yellow, that's a future reference signal prepared according to the absorption shape to represent the characteristic of the waveforms. It's possible to represent a waveform with a large amount of the data with only 12 data points without losing necessary information. This is an example of the how to create database. So as explained, we prepared almost 12 difference data. Red one is our target signal. Blue one is the interference signals. Just showing the one component interference, but we can set 3 or 4 components of the interference. Blue is just one, but we can create 3 or 4. Then green one is a wave number shift. It's a temperature effect. Then yellow one is a broadening. It came from the pressure. So then how to create our database? We set this red one. It's a target gas. For example, ethylene 10 ppm. We following the ethylene 10 ppm. Then other factor, other parameter changed. So this means the broadening, yellow one changed. Then this one is wave number shift is changed. And this right graph showing the interference database. We set the interference like S1, S1, then we change the temperature and the pressure as well. So in advance, we created like this database, then we installed the customer side. That is our database creation. And this is the actual calculation. RM apply the matrix operation. Then in this equation, correction is including such as wavelength shift or broadening factor. The feature quantity are proportion to concentration, but if spectrum is influenced by the broadening or wavelength shift, it becomes non-linear. So RM repeats the matrix calculation with the correction against the broadening or wave number shift. We convert value by repeating the calculations. Okay, from next slide, I show the test result using our RM technology. So this is just showing stability almost at 1 day, 24 hours. So just measurement the nitrogen for the ethylene is a left graph, CO2 is a right graph. The y-axis is a 2 ppm, minus 2 ppm and plus 2 ppm. So it's stable for the 1 day. And next show the response time. This one is flowing 0 to span. Right side is span to 0. The span gas is a blending gas. And this one is vibration test. We tested X, Y, Z direction. So this result showing the stability. So it means no misalignment. It's robust, it's achieved. And the next slide, I showed the field trial result. We installed the ethylene plant. Then we almost testing 6 months, 7 months in the field. So this is one upset condition data. Then this gray one is ethylene. Yellow is CO2. Blue one is methane. orange is methane. Then around 6 a.m., suddenly methane is spiking. It's upset condition, but acetylene, gray one, and CO2 is stable. It means no interference effect for the acetylene and the CO2, but orange one is after spiking, little bit moving. It means gas condition is different change, but ethane is catch this trend. This is good result in the field test. And also, same data, above data is the same data in previous page. Then the other one, bottom one is we compared general QCL analyzer, but same yellow is CO2 is moving. I think it means interference effect in the general other analyzer. But our analyzer is stable. That is good result as well. And also, this is another trend. March 2nd, same upset. Methane is upping almost 800 ppm, but yellow and CO2 is no change, no interference. But as a QCL, it has an interference, I think. Okay, that is my conclusion. We developed a new gas analyzer and a new technology, so achieved high sensitivity and fast response, then obtain good test result in our laboratory. So, and also field test trial in the SLM plant was good result. So acetylene, carbon dioxide were stable in the upset condition, then catch up a quick impurity. So next, our target, expanding more component and also application, SLM feed or caustic tower, and we trying to new market on the carbon neutral. All right, that's all my presentation. Thank you so much.
Okay, next we have Adam Wilson. He's with Kite Industrial Analytics, and I'm going to let him introduce himself. So, thank you. Take it away.
Well, so, as I say, my name is Adam Wilson. I'm an applications and data scientist working at Kite Spectrometers. I've spent a lot of time working in chemistry and academia. Got my PhD in supramolecular chemistry at the University of Edinburgh. And then after that, and a bit of stint in postdocing in various fields like organic photovoltaics a long time ago. Moved into industry, got some interest in statistics, data science, and that's brought me to Kite, where I'd like to present some stuff about measurement of organic acid buildup in glycol dehydration of water by mid-infrared, exploring the need for nonlinear calibrations, and static optics FTIR spectroscopy. So, what are we actually presenting? Like that. There we are, perfect. Okay, so who are we? We are Kite. I have come here from Oxford, highlighted in the map down there. Thank you very much for having me, Texas. It's my first time in the United States. I've been made to feel very welcome. Our office there. And we are a spin-out from a UK government project trying to do space research. We start out as a company with the idea of sending a spectrometer to Mars. Requirements for a spectrometer that you need to send to Mars, it needs to be extremely robust. It's the kind of thing that you can hit with a hammer if you need to, so that it can be launched into a rocket where there's a lot of vibration and take it to the most hostile of environments. Didn't get to Mars in the end. Instead, ended up going to pipes in our chemical industry, and we've been using it to perform various different analyses. Part of my job is to assess new applications as they come in, to say, is this something that we can measure using mid-infrared spectroscopy? One of the ones I want to talk about has come from Scotland, which is a hydrocarbon application that we thought that might be able to use our process. So what they have here, this is for the dehydration of ethylene glycol. So what they have is they mine natural gas, which comes out of the ground, you probably know better than I do, completely saturated with water. We need to remove the water from that. What they do is they bring it up through a system here where they've got contactor trays containing monoethylene glycol. That sucks the water out of it, monoethylene glycol being highly hygroscopic. And that comes out the top there and goes on out. Do we have a pointy pen? We do have a pointy pen. Yeah, it comes out the top. Okay, so then the ethylene glycol needs to be recovered. And at that point, it's full of water. So what we need to do is take that water out and monitor the efficiency of the water recovery so that the water can be recovered and so that the ethylene glycol can go back into the system. So we don't know exactly where the client was intending on putting our instrument. We suspect it was either before the recovery boiler to monitor how much energy is going to be required to take the water out, or possibly after it to see how successful that has been. But either way, we want to see how we could, whether or not we could use it for that application. So, let's see. They provide us with a specification of different chemicals and different chemical concentrations. So the system they wanted to look at consists of monoethylene glycol in that kind of concentration. And what we have here is some amount of water in it. So the water can be either lean, containing very little water, that's after the process, or it can be rich, where it's been saturated with water by the process of removing it from the natural gas. It also contains amine. We do not know what the amine is, it's proprietary, but they've asked us to look for it in concentration of 0.1 to 11%, or 50% weight volume for a particular application that they wanted to be looking at. There's also, present here, so the amine is there as a corrosion inhibitor, and the things that it prevents corrosion by is the acetic acid, the formic acid, and this salinity here, so chlorides that have been floating around in there that we need to assess to see whether or not they can be taken out. So how would you measure this process? So there's a number of different techniques, and we've seen many great examples of some of them that have been available today. One of the most obvious ones is going to be using things like GC, where you go in, you grab a sample, you process it, and use a column to separate out all the different chemicals and analyze how much there is in there. The advantages of that is that you do get to see all of the species, all nicely laid out. It can take time. It's not a fast process, so that can be difficult. And also there are safety implications for having to perform grab sampling. It can be quite difficult to do that. There are also techniques which you can do simply online, seeing things like pH, temperature, oxygen levels, various different sensors that you can use from which you can infer other things going on, typically measuring just one thing, and you can use that to work out what's going on, but the information coming out of it is something that you would have to use in conjunction with your chemical knowledge to find out what's actually going on inside your process. In the middle here, we have spectroscopic measures. And there are a full raft of things we can use here, which have the advantage of they're right in your system, they're monitoring in real time, and you're able to work out precisely what's going on inside because it's able to see all of the different chemical species all at once, and so you can analyze those. So I'm here to talk about a potential application in mid-infrared, which has been an unusual one for something like this. So often people will go to something like near-infrared for an application like this. And the way that you'd have that is you've got an emitter down here, and then you've got a flow cell or some kind of sample cell where you're able to pass light through here. You shine infrared light back, and it comes back, bounces back down off a mirror. And the absorbance is used to work out what's going on there. That builds up your spectrum. That's the ideal situation. The reality is often made more complicated, as we saw for those of us who were in the sampling lectures that was going on yesterday. There are presence of bubbles, there are particulates, and those can cause scattering effects, which can be problematic for an analysis. So one way that you might consider going about this is using mid-infrared. That's this stuff here, and you're using something like an ATR probe. So rather than using a transmission cell, we have a sliver of diamond down the bottom here. The infrared light comes out the bottom here, interacts only with the very tip of this. So the penetrative depth is measured in microns, which means that most of this stuff that's floating around in here is not of any concern to us. We only see the stuff that is in intimate contact with the diamond probe here. It comes back here. And using mid-infrared allows us to use the most information-rich part of the infrared spectrum. We've got lots and lots of peaks here, which you can able to use to pull out what's going on inside the process. Okay. There is a problem with mid-infrared, and that has to do with robustness. How do you get the device where it needs to be? What are the problems you face with that? So what we have here is a standard Michelson interferometer, and you can see here the way it works. So the light comes in through here. You've got a semi-silvered mirror. Some of it goes up here, bounces back through into your detector. Some of it passes through and interacts with a moving mirror. That mirror is moving very rapidly backwards and forwards, and that gives you the interference patterns that you need to deconvolute into a spectrum. Okay? The problem with this is what happens when you take something that is designed to vibrate and put it next to something else that's vibrating. If you take most of Michelson interferometers and you put them next to a pipe in a chemical facility, the vibrations would cause the spectra to be a complete mess. It shakes it around and causes interference patterns that you're not able to deal with. One way you could get around this, and you see this in near-infrared things, is by taking the spectrometer and moving it far away. So what you do is you have this out of the wave where it's going to be vibrating, and you have a fiber optic cable that links the two. The trouble with using this for mid-infrared is that the materials you use to make fiber optic cables attenuate infrared light very seriously. So as the stuff comes out here, it's all well and good, but then as it comes back, you end up with not very much light coming back in to do your analysis. So we've got to have a problem here. How do you deal with this? How do you square that circle? The way that we've gone about it is by dispensing with moving mirrors. We'll come back to that in just a moment here. This is our piece of kit, which you can see down. Please do swing past the booth if you haven't done so already. Here in all its squat utilitarian glory is the IR Armadillo. It's a small box. It's about this big, with the probe extending to about this big. It goes directly into your pipe, and it's in a rugged aluminium box, which can take a real beating. The reason it can take a beating is because of its optics. So we do not use a Michelson interferometer. We use something where you've got a proprietary series of mirrors here, which are curved surfaces here, which I'll take you through. So basically, what we have here, the probe is a hollow tube. There are no fiber optics here. It is completely empty. We've fitted with industrial purge gas to remove water vapor. But the light is emitted by an emitter here. It goes down here. It makes a single bounce, as we showed in that diagram, where it interacts with the material that's in your probe. So this is directly in your process, and it's in intimate contact with the process fluid. It bounces back here. Again, it passes through a semi-silvered mirror. But instead of using a a vibrating mirror, it uses a series of curved mirrors here, which generate a two-dimensional interference pattern up here, at which point this computer, entirely contained within the device, performs immensely complicated maths, which I have absolutely no idea, but the output of it, we put in a series of chemometric models, which then spits out the chemical concentrations of interest. It has no moving parts, and so can be taken pretty much anywhere. Ooh, I wonder if I'm going to be able to play this video. Pity if not. No, we're not. Okay, well, it's immensely impressive. What you see here is, so we're at a site which has got, we're at a facility just outside Oxford, which does lots of aerospace stuff. What we have here is a vibrating table, which shakes the instrument. So this video, which in all its cinematic glory, would show the spectrometer bouncing around at about 5 hertz. And this thing here records what the spectra is seeing, and you can see that there is no change to the spectra whatsoever. So this thing is just leaping around, and it doesn't seem to affect it. If you, then what we do is we ramp this up from 5 hertz to 6 to 100, so it's sort of oscillating faster than you can see, and it has absolutely no impact on the spectra whatsoever. You could put this directly next to a pump, completely adjacent to it, or touching it. It will not bother it. It's perfectly fine. And it's been ATC certified, so it means you can put it directly in the pipe, which dispenses with the need for those fiber optic cables, which would mean that you wouldn't be able to bring it into the pipe. We have frozen. Folks, I'm out of ideas because I'm just seeing the spinny blue circle here on the screen, so I don't know what to do next. Brief intermission. You may talk amongst yourselves for a moment. Good. Beautiful. Okay, that's great. Thank you. Thank you very much. So what that means is you can now take this instrument into places where you can't take other instruments. Here we have it in a series of industrial applications. We've got it plugged directly into the pipes in the middle of the factory process with no need to lay expensive fiber optic cables to carry the information around. What we have here is quite an old picture now, where we had a conditioner system, which would allow us to take the samples down to a temperature. This was only a formality as far as we're concerned. The instrument had not been formally certified as being tolerant to, I can't remember what it's up to now, 220 degrees Celsius. So we required a conditioner just for legal reasons, but in fact, it's completely robust to those kind of temperatures, pressures, whatever. It can be taken anywhere. As you can see it here, I mean, I think some of these are ethanol applications. We have a cradle to take it in and out, which means that you can deal with all of the problems that would come from ordinary things here. So how do we build our chemometric models that would allow you to take a spectrometer and turn it into an analyzer? So what we do is you have it plugged into your pipe, and it records spectra once every 2 minutes. What you also have at the same time is you'll be using your standard process control techniques, for example, an HPLC. And what we do is you take the results that come out of this, we marry them up with time-stamped spectra that come out of the machine. We use that to build a chemometric model that associates the concentrations coming out of this with the spectra coming out of this. And what we end up with is a chemometric model which produces this nice straight line here of measured concentration against predicted concentration. And then once we've got that, we upload it to your system, and that's good. Where does the data for this kind of thing come from? How do we make these models? They can come from 3 sources, and usually we do a combination of the 3. The best, overwhelmingly, is online process data, where you take it in and we actually look at the spectra that are coming out of, for example, the recovery boiler in our application. You put it in there. If there are similar applications, what we can do, or if we have data from other installations in similar facilities, what you can do is you can combine that data with other things from other applications and smoosh them all together to make a general model that suits across many different instruments. More relevant to what we're going to be talking about here is the proof of concept stuff, where what we do is you've got a little thing that sits on the front here, which is a sample cell. We make up artificial samples for proof of concept lab tests. The idea is that you make this here to give you the range of concentrations, then you fill it in with online process data, and if you need more, then you can add data from other installs. And this is what allows you to build the model, as you can see here. So our client wanted us to build a proof of concept work that they can demonstrate it. And rather unusually, they wanted to do the analysis themselves. Normally, we do it in-house. So in tandem with them, we developed a set of mock-up samples in which they provided us with their proprietary amine, and all of the rest we provided ourselves. So we put these things in here. So we developed with them a list of concentrations that would replicate broadly representative things of what the lean monoethylene glycol and the rich monoethylene glycol that's got a much higher water concentration. We put those in, we obtained the spectra, and they reported those spectra back to us, and we went about and built some chemometric models. So let's have a talk about how that looked. So here are some of the spectra. This is just a small subset of the spectra that they took, but it shows the main points. You can see many different peaks here, many of which correspond to different species here, and they're all overlapping, so it's quite complicated. Univariate models wouldn't be any good here because there's so many overlapping species, so what we tend to do is we go straight to partial least squares as our first line of attack. So what we do is we look to see which spectral features relate to changes in the concentration of the things of interest. So the output of partial least squares, I don't know how, I'm speaking to many chemometrics people in the audience, but basically the output of partial least squares is a series of loadings. So these are mathematical constructions that show orthogonal variation in the different species that are being done. So what we do is as we increase the water concentration, we see more and more of this spectrum being added to it, and this spectrum, rather less of it, and then rather less of this spectrum here. All of the variation that is accounted for by changes in water concentration is made up of these things, or about 90, can't quite see, 90-something% of it. And although these are mathematical constructs, you can relate them, in the best cases, to actual chemical changes. So as we add more water, you can see more of this water peak being contributed to the spectrum. What you can also see, which is quite cool, is this negative peak here, which is the loss of monoethylene glycol, because if you've got a large amount of water in it, some of it is going to be taking up space that would have been provided by the monoethylene glycol. So as you add more water, the monoethylene glycol goes down. That's the thing. This loading here contributes 94% of the variation that comes from water, so you know that this thing is going to be very important going forward. This one rather less so, and this is good. So what we then do is we do this for all of the different species and see how well they do. And we plot these things, and here are the nice diagonal lines that we're talking about. So here we have our measured values and our predicted values, and you can see that these fit rather nicely along here. So for species such as monoethylene glycol, acetic acid, formic acid, and water. What we do for this is we apply the first derivative. That helps to take out variations in the baseline and possible temperature effects. It doesn't take them out completely, but it takes them out to the point where you can neglect them. We validate these things using cross-validation. Well, what we do is use a Venetian blinds method where you take out some data points, we predict from what's left, we build a model on the points that remain, then we predict the points that we took out, and we repeat that many, many times and take the average of that so we can see how much variation there is. It's a check for the robustness that we can do. And you want the RMSE-CV to be as low as possible. That's root mean squared error of cross-validation. And these things are all nice and low, demonstrating that we're getting good models coming out of this. And this tells you how many latent variables are in it. These are the different loadings that we had, and you can see some of them for acetic acid, we only used one, which is a good sign that this is going well. But it wasn't all good. Not all of these were ideal, and we weren't really happy with the error in the formic acid one. You can see there's quite a lot of spread around here, a little bit less than the acetic acid one up here. So we wanted to see if we could do something that was a little bit better. And for that, we moved on to what is our standard next line of attack, which is support vector regression. If I talk about support vector regression, how many people know what I'm talking about? You know, nod your heads, look blank. Okay, good. Oh, I'm in trouble now. Okay, fair enough. Okay, so my understanding of support vector regression is, so we contrast against ordinary least squares. So when we're presented at school with some points on a grid, you want to draw a straight line through that. Intuitively, you just draw a line that captures all of this, and you find out that later on, as you go through your mathematical career, you find out that what you're doing is you're minimizing the sum of the squares of the residuals all along this curve and all along your data. So all of the distances between here and here, you want to get that as small as possible. And when you do this, following the algorithm for method of least squares, you get the single correct answer for this. There is one line that goes through this, and that is the one that leads to the minimization of the sum of the square of the residuals. Is that the best model? Not necessarily, actually. Because you're getting a sample of the data, not all the data itself, what if the sample was being biased by large amounts of data? For example, at this end, you see that a whole bunch of points here, which the line has felt the need to go through in order to minimize all of those residuals. Is that necessarily the best way of going about this? Do you want something a little bit better than that? One technique that you could use to get around this problem is something called support vector regression. Now, with this, what you do, instead of trying to minimize the residuals of all of these data points, what you do is you fit in a line, and you fit in a buffer region around it, defined by this term epsilon, in which you don't care about the residuals. You ignore them, you don't care. What you do instead is you take these points on the outside, which you call your support vectors, and these are the points whose residuals you try to minimize. And that is what you do in order to do something which is less weighted towards some of the more concentrated data points here. So there's a whole bunch of ways that you could do this, and there's different values of epsilon that you could use in order to make your thing more or less sensitive to this. And there's also costs and various different features, like how much do you weight the difference, the penalty for having a high residual. How do you know what the right one to do is? Well, you try them all. You do very large numbers of hyperparameter tuning, in which you've got your cost, your epsilon, and your gamma. These are different things which change the parameters of how you fit these models. You exhaustively search for many of them, and what you end up with is this nice grid here, and you use the RMSE CV for each of these to find what is considered to be the best set of parameters for that. And what we found out is, for this one, this felt here, that's what we're going to do. We use that, and we predict some test data to do that. What we find is that for some of these species that were in our application, where we felt that the PLS models weren't sufficiently good, we did a lot better when we used SVR, and there's not a line of best fit here, but you can see the variation in here has been reduced quite considerably by using SVR. So we think that that's a much better model for this, and particularly for acetic and formic acids. We believe that those are intrinsically harder to model because of the changes in pH. When you have these things at different pHs, then you're actually dealing with multiple different species. You're dealing with the acetic acid and the acetate in equilibrium with each other. We think that that is what is making these slightly more difficult to model, and these benefit from having SVR to use them. This is all summarized here, in which you've got the different species that we're looking at in both the rich and lean systems here, and you can see here that many of these PLS was fine. Some of them were improved when we used support vector regression. Some of them were, 5 minutes, okay, we'll go fast. And my final slide was this odd one here, which is about salinity. So infrared requires a bond, as we've seen before. How is it that we're able to measure salinity in something? How are we able to see ions? And that's an unusual one. And we have seen this in a couple of times. We have an application in lithium mining in which we're looking at measuring lithium in water. And what we see here is that we forget that water is a structured liquid. There's all sorts of bonds. What you have here is a network of hydrogen bonds all linking together. If you add ions to that, then you can either improve the amount of linking that goes on and the amount of coordination that is, or you can have things that disrupt it. This is largely governed by the ionic radius and the charge density. These are things which provide actual infrared signatures that you can measure, and you can find out how well these things are going on. So as we can see here, there's a paper where people looked at this and found out that you can actually see things like chloride in water by infrared. This is fairly early stage stuff. We would like to do a lot more in it, so if you've got a lithium application, we'd love to hear from you. So these are the things that I want to talk about just now. So we've got static optics. So this has been essential for getting the things into the system where you're going to need to operate it. So if you're struggling with Michelson interferometer, static optics is a really useful technique to get around those problems. We've seen here that you can use well-designed sets of artificial samples to perform your calibrations. We've seen that they've got models have been very effective using PLS, but in other situations where you've got things in equilibria, it can be quite difficult, and so we have benefits from using things like SVR, and these can give very useful improvements. There are other techniques that you can use as well. We sometimes use things like locally weighted regression and so forth like that. And there are species without intrinsic infrared spectra which can be monitored by looking at the structuring of the water as well, and this is something that we'd love to do a lot more work with in future. Which I think about wraps up for me. So do swing past the booth if you haven't already, and thank you for having me. Thank you.
Okay, where's Nate?
From the diagram, looks like the the light only touch a small portion of the liquid. Approximately how depth the light can go into the liquid and do the measurement?
I don't know the number off the top of my head. I have optics people who can tell you, but it's in the microns. So it doesn't penetrate very far.
Okay, since the micron range, that's a very small portion.
Yeah.
Is that the detection limit compared to the traditional one, MIR, which have a millimeter? Is that the detection limit much lower?
Yeah. So signal to noise is something that took quite a long time for us to optimize and get up to the levels we can. We haven't typically been limited by it, and so it's not something that we're worried about. But it seems to be working well enough for us for the time being for certain applications. If you wanted to go higher while still maintaining the same technology, there's various different things you could do, like having multiple bounces on the probe to make certain it bounces out. R1 makes a single bounce, so you only come into contact with it once. Other designs are possible. It's not the ones we've gone to, owing to other technical constraints.
One more question related to that, because
Sure.
you only touch a very small portion on that surface. Is that the flow matter? Is that you prefer more like turbulent flow of those liquid, or you, for the application, the laminar flow?
Yeah, so we average over 2 minutes, so we do see quite a lot of variation with your fluids. We're not seeing a static picture of it, we're seeing something that is averaged over a period. Now, whether or not you require turbulent flow over laminar flow, that's another discussion. We tend to find that we certainly would like it to be in the turbulent regime, just so that you can get this swirling representative thing. It isn't something that we've been aware of being a problem where we found ourselves to be in the laminar regime for most of our things, because most of our things are fairly, are not super viscous.
Okay, thank you.
Okay.
One more last.
Yep, go for it.
Supporting better regression. When you said it's better, actually, do you do the validation or cross-validation?
Yes.
To isolate some data for testing?
Yeah.
That's
So,
why you said-
yeah. So this is only proof of concept work. Our typical routine for doing this is we would ask customers to provide us with data that comes out of the thing in their pipe. So they report the spectra and concentrations that they have. Then what we do is when they send us some some concentration measurements, we withhold some of them from our model building process. We don't look at them at all. We build our models, and then we blind predict those to see how well they're doing. I wasn't able to present any of these here for this application because we didn't get that far with it yet. But for our standard process for all of this is to do validation with a set of samples that we're blind to. And then that goes on a rolling basis because models need updating from time to time because process changes or whatever. So our first step is when we get some new data in, we validate our old models against it, see how they're doing, and then if necessary, we rebuild.
Thank you. Thank you for the detailed
Okay.
answer. Thank you.
Thank you.
Thank you, Adam.
Okay.
I appreciate it.
Thank you.
Yeah, while they're getting that together, I wanted to give you information on the authors of this paper are Nate Watson, David Pinkerton, Todd Vacicek, Jizu, Joshua Christian, and Paul Little. And Nate Watson is going to do the presentation on real-time batch interface detection and transmix reduction using infrared spectroscopy and machine learning algorithms. So this is a revisited paper, it's one that's been done before. So anyway, I hope you all enjoy.
Like we're good. Okay. Am I on? Yes. Okay. So we burned a good 7 minutes, but lucky for you, I'm fast. So you'll still get to go down and hang out in the exhibition hall. So my name is Nate Watson, and that's not causing any problems here. Hold up. Sorry, the computer's doing something. Let me just make sure it's going to let me go. Okay, we're in business. So, my introduction didn't make it in time. My name's Nate Watson. I work for JP3 Measurement. I'm an analytical chemist, which means I like to measure things related to chemicals, and I like to solve random problems related to that. So working in near-infrared spectroscopy or anything like that's good for me. In my previous life, I was in the US Army where I worked in artillery and nuclear weapons. They're the ones who got me all my education in analytical chemistry, because nuclear weapons and analytical chemistry surprisingly have a lot in common. And I live in Western Montana with my wife and 4 kids. So that's me. What I'm about to give you here is a presentation on pipeline batch interface detection, a method we have for doing that. If you were here last year, I gave a similar presentation to this, but we've added some extra field experience that we're going to elaborate on here. But I'm going to go through some of the background first so that everybody knows what I'm talking about. And fortunately, the previous presentation, also dealing with optical spectroscopy, covered some of the details. Those procedures that he talked about, partial least square, support vector regression, all that kind of stuff, is pretty generally applicable to most optical analyzers. So all that stuff applies too. So retain everything he said, and a lot of it applies to me too. So here we go. Again, we're going to talk about what the actual problem is, what we've come up with to work with it, and then some kind of extended automation tuning options that we've implemented to help make it even better and more robust so that the operator has less to do and it can be more of a just, here's the thing, plug it in, it goes. So anybody that works in the pipeline business is aware of this problem. This is the batch interface problem, whereas I have one product here, another product here, and in between is this stuff that happens when they flow through the pipeline beside each other and they mix. And again, looking at more detail, I've got these products here. I've got gasoline, and I've got diesel, and I've got this interface product that's no good. I can't do anything with it except to send it back to reprocess it. But I want to minimize this as much as possible because diesel fuel is worth a lot of money. Gasoline is worth a lot of money. The green stuff in the middle, not worth a lot of money. But the simple solution is just say, well, I'll just throw it over here. I'll cut a huge chunk out of the middle and send that back for reprocessing. But when you do that, you take what is a lot of good product and send it back for reprocessing, and you've just wasted money, both in shipping, product you didn't sell, so on and so forth. So our goal is to use tools to automate a solution so that you can cut this valve switch as close as possible to the end of pure product. So you put his absolute highest amount of pure product into the pure product tank, and you put as little as possible transmix into the transmix tank, which has to get shipped back. So that's the general problem. Now, I work for JP3 Measurement. We sell near-infrared analyzers. So our solution, of course, is going to deal with near-infrared spectroscopy. But all the methodology I'm about to tell you will work for any optical spectroscopy. And you could use this thing that we made and plug it into a UV vis or a mid-IR. Heck, you could even use a GC chromatogram, and it would all work. Now, in most cases, if you're doing this, you'll want to focus on speed, because in some cases, minutes relate to huge amounts of dollars, and I'll get to that as we get later on. So the key feature is you need a measurement tool that can tell the difference between all your different products. And what I have here are near-infrared spectra of, the green one is premium gasoline. You can see it looks different than regular gasoline, which looks different than diesel or jet fuel. So you need a tool that can tell the difference between the chemical composition of those. All of these absorption spectra are related to the direct chemical composition of the product. Diesel is made up of, the C10 plus kind of alkanes. Gasoline's the C5 to C9 kind of alkanes, so they have different spectra. I can do that. A gas chromatogram would have a different layout because of that same difference. UV vis probably would work. Choose your optical spectroscopy, it would probably work. And usually we recommend optical for this kind of thing because it's faster and more robust. And what I do is I take these, and instead of using all of these points, you can see that there's all this stuff here that looks pretty much the same, and then there's all these features on the right that look different. And I basically do something like our previous presenter showed you, and I'm not doing regression, I'm just doing decomposition, which is saying, look through these, compare them, and focus on the stuff that's different, or focus on the stuff that's different between the spectra, and plot it in reduced dimensional space. So this is in 881 dimensional space, and down here I have it in 2-dimensional space. So I did a mathematical projection to take complicated spectra and put them down into simpler space, and the more different they are, the farther apart they plot. So you can see over here, here's my diesel, it's the most different from the premium and the regular. It plots way over here, and then in between is the regular gasoline, and there's the premium. Farther apart, the more different the spectra are. I'm going to use this simple decomposition and a little bit of an automated algorithm in order to make a thing that'll basically tell you pure product, not pure product. You want to put that into the transportation mix tank. And the way this works is you've got your new spectrum comes in, and I'm going to have to end up staying over here because I can't see what I'm doing. So I've got all my previous spectra. Let's say this is all pure product 1. We'll say it's diesel. And every time I get it's still diesel in the pipeline, I'll do that operation, and it'll plot on top of the rest of the diesel because it's the same spectrum. Eventually, when I get to that transportation mix, when it starts flowing through the point where my sample point is, it'll start plotting farther away because, hey, it's different. I get a new spectrum, I draw a circle around it, and I set some distance that says, once this new spectrum, more than some percentage of the points are not in the circle, hey, we've changed. Now you need to actuate the valve, either automated or somebody will say, hey, look, the thing on the Modbus control says 1. I need to push the button to change the valve. And then I keep monitoring it, and I do that every scan. Some other ways to look at it. I'm going to go over here this time. Keep everybody thinking, mixing it up. So I get my spectrum. This is a diesel spectrum. I plot it. There it is. It plots on top of all the other spectra, all the previous spectra. They're all within the circle. I say, hey, look, it's a pure product. And then I take that spectrum, I put it in some sort of classification model. This one here, I'm using the k-nearest neighbors on PCA decomposition. And I say, hey, look, it plots here in the diesel cluster. Output that it's diesel. And you can put on the screen that, hey, it's diesel. And then eventually, I get this spectrum, which doesn't look like that spectrum. And it doesn't look like that spectrum. It's the stuff in between. It looks like a 50-50 mix of diesel and gasoline. And it plots over here. And when you draw the circle around it, there's no other points in the cluster. So therefore, it's in the middle of some sort of changing that interface mix. I say, hey, look, that's transportation mix. And I keep doing that as I go along. And I also don't classify it because if it's this transmix, I don't care if it's mostly diesel, mostly gasoline. It's just junk. I put it into the junk tank. And then eventually, I get through and I get over here to where I'm in pure regular gasoline. There it is. And it's no longer changing. All the points are in the cluster. Call it pure product. Do the same thing. It plots within the gasoline cluster, and I call it gasoline. So that's the general idea. It's pretty straightforward. I'm going to automate it here. But when we get to the end, the key feature that we're going to start, the kind of novel new stuff here, is related to automate, because I said just there's a circle. But you need a radius of that circle, and it's in multidimensional space, so we'll call it a spheroid, because on a 2D plot, it's a circle. In a 3D dimension, it's a sphere. In 4D, we don't have a word for it that I know of, but it's a sphere thing in 4-dimensional space, or 5-dimensional, however many you need. And that's how it works. But here, I'm going to walk through how this goes. So here's the gasoline. There's my little arrow showing gasoline. There's my cluster. All the points are in the cluster. I keep moving along, and I get to this edge of where the gasoline and the diesel are mixing, and I have this interface, and I get this new point, and it's plotted. There's a virtual circle around it. It's outside of the cluster. I say, hey, new stuff. Call it transportation mix. Now I monitor. I'm in the middle of the transportation mix. I can see that the points are still plotting. They're moving along. They're no longer in the cluster. Not good product. Eventually, I get into good product, and after the concentration of points in whatever the parameter I set is, I say, hey, it's diesel. Shut the valve over to the diesel tank, and let's go. In automated, this is what it'll look like. There's my new spectrum. There's a circle. Got past the coverage in the circle. Say, hey, interface. Next one comes in. Still no other points in the circle. Keep doing it until I start clustering again. There you go. Diesel. Make sense to everybody? You can feel free to interrupt me whenever you want. I kind of like it that way better. But so I gave pretty much the same presentation. I give this to anybody who wants to use this kind of algorithm. And what we're going to do now is look at a couple real-world cases of real field data and kind of how this works. So the real key is that circle size, because you would think, hey, everybody's got the same thing. But it turns out that every customer has a different secret sauce they want to use for how they do this. That some people, their tolerance, because you have a big storage tank. You can accidentally ship a little bit of diesel into your gasoline and get away with it. And depending on pricing, maybe they want to do that a little bit, or a little bit of transportation mix can get in the gasoline to some tolerance that doesn't foul the tank. The diesel tank has very little tolerance for gasoline, but you still want to be as close as possible as you can without failing your physical property test, so that when somebody comes and draws a sample from the diesel tank and runs a flashpoint analysis, which is, if you're familiar with diesel, flashpoint analysis is take a little cup, put some diesel in it, heat it up until it lights on fire. Flashpoint. The temperature where it lights on fire is diesel. That's flashpoint of diesel. Usually it's 140 degrees Fahrenheit, something like that. Jet fuel has a little bit lower. Gasoline lights on fire at room temperature, which is why it's more fun if you ever light a fire at your house. I live in western Montana with my kids. If you want to have an experiment, you're lighting all your brush on fire to get rid of it, put diesel on one, put gasoline on the other, and kind of stand back from the gasoline and throw a match, versus the diesel. The gasoline's a lot more exciting if you have fun like that. Sometimes it can be fun. Anyway, so here's the data. So I have here a transition that we were monitoring. So we're going from summer conventional before octane blending gasoline, or before oxygenate blending gasoline. We have the transmix, and then it's going into jet fuel. So when we're running gasoline, we also generally monitor the density as API gravity. Well, this is API gravity. We also monitor the octane number, and all of those can be done through partial least squares calibration. Then you have your flash point here when you get to jet fuel. Jet fuel's, gasoline's usually controlled based on octane number, and vapor pressure. Jet fuel's usually controlled based on flash point. And then this purple line here is what we did with our kind of default circle size using the interface detection algorithm. You can see it says pure product, and then here, as the octane number starts going down because the jet fuel's mixing in, eventually this thing cuts. Well, here you can see that's about 922. Well, the customer said, we really want to cut, we can take this much, it can get a little bit closer. We can deal with that in the gasoline tank. So they said, we think it should be here. So this is us tuning that circle parameter so that we get what they want. But it turns out that circle size isn't fixed. You need a circle size for when you're going from diesel to jet, or when you're going from gasoline to diesel. You need a circle size when you're going from every product to every other product, because it could be different. It also varies with flow rate. Now, for this particular customer, they flow at 8 barrels a second. So we're talking 6 minutes difference here. 6 minutes times 6, that's 360 seconds. 360 times 8, that's a lot of barrels that you would rather put into your pure product tank to make money as opposed to put into your transmix tank. Now, that 8 barrels a second is the fastest pipeline flow that I have any experience with. A lot of them don't run that fast, but still, even 1 barrel a second, a couple hundred barrels is a lot of money. So that's what we're doing here, is trying to do this tuning period, and that's this is one case. But the key critical piece here is that in order to know that I'm going to jet fuel from diesel, I have to have some other piece of data. Because all I know is what's in the pipeline right now. I don't know what's going to be in the pipeline. I could have a batch schedule and somebody has to look it up, but if I'm trying to automate, I don't want to have to sit there with the lookup table and try to figure it out. I could have these physical property models which start to kind of give me some indicators of that still tells me when I'm getting to the pure product. I want to know what I'm going to. So the solution we've come up with is you actually have something else upstream that'll inform, hey, there's going to be diesel here in 45 minutes. And that gives you, because the batch schedule can be wrong. Sometimes there's hiccups in the middle of it. The next one here you'll see is going from jet fuel to a summer gasoline blend to a winter premium blend. And you can see the same thing, but you see right here at the beginning, there's this weird hiccup. There was they had some other stuff here in the pipe. It looked like it might have been a little bit of diesel. There was something going on, and the upstream will give you a little bit more information so that you can say, hey, we're going from jet, and then we're gonna go to this summer RBOB, which is a regular gasoline product. And I know that I want to cut here so I can tune this parameter. You can see on this one, our default size was a lot different than what they wanted. So we took a little bit of time tuning. Same over here, as we're going from summer to premium, you notice there is no transmix, there's only one line. It's when you cut from one to the other, because you can put as much premium gasoline as you want into the regular gasoline tank. Nobody will ever complain that you're giving them 93 octane gasoline at 87 octane prices. They're happy to do that. But at the flip side, you as the operator want to put as much of the regular gasoline into the premium tank as you can possibly get away with without putting your octane number below the threshold, because every barrel of regular that you can slip into the premium tank, you made whatever the delta is in price. This is the whole oil and gas industry, as far as I can tell, is about sticking butane into places so you can sell it at gasoline prices, sticking ethane into propane so you can sell it at propane prices. There's all these kind of slip the low quality product as much as you humanly can within the rules to get as much money as possible. That's what we're doing here. And like I said, we're all analyzer people. Yes, go ahead. 5 minutes, I'm almost done. In fact, I'm about to be done. So looking at this last one here, that's my last slide, I promise. Looking at this last one here, this is this data decomposed into principal component space. And you can see here's the jet fuel, here's the transmix to where the line is with the summer regular gasoline, and then here is the premium. And these are all the optimized cut lines. And what we would use is we use these spaces here to determine the circle size. So run some calibration, do a plot and say, hey, this is what we want it to be. And I say, hey, this is the circle size, it needs to be here. You can see the circle sizes are different at each one. So that's kind of what we're talking about here. And ideally, we're going to make a whole lookup table of all the possible transitions with the parameters that you need, load that into the computer control system, and then you say, hey, we're getting ready to go to jet from gasoline. The parameter is going to be this. Let the system go. And that's it. What are your questions? I adhere to the keep it simple, stupid principle. So simple is always better than complicated, which is what our goal is with this.
Any other questions? Okay, this concludes session 3, and we're going to have a break from 2:45 to 3:30 so you can have time to go visit the exhibits. So thanks everybody for attending this afternoon.
know, I think I'll pack my rags and move on to some other town. Now, when I had money, all of the party was all on me.
All right, we'll go ahead and get started in our final session of the day here. Keep us on track. Thank you all for hanging in here and coming in on the last session here. I want to introduce our first speakers. First speaker is Michael Hoffman with Siemens. He's a strategic support specialist. His initial introduction to the industry was with Standard Oil BP for 26 years, working with instrumentation, analyzers, analyzer data management, safety, and implementation of analyzer technologies for various processes. With Siemens since 2007, with responsibilities for digitalization, analyzer management and monitoring software solutions, smart sample systems, sales support, and customer service response. His hobbies include traveling and his grandchildren. And co-presenter on the paper is Chris McGarvey with Dow, who is a process analyzer technologist. Chris began with Union Carbide in 1990 at the Texas City site. Soon after the merger of Dow and UCC, Chris moved to Dow, where she has worked in multiple process analytical positions around the Gulf Coast. Chris's experience with a variety of process analytical technologies, but for the past several years has focused on process analyzer reliability and data quality. I'll turn it over to Michael.
How about now? Oh, I even heard myself that time. So thank you for coming this afternoon. It's been kind of a long day here at ATC. We're going to talk about some really neat things, and I want to share with you some of the stuff that we've seen. We actually have a unique relationship with the industry. When you talk about what we do in the analyzer community, the reality of it is we provide data to operations. We provide data to operations. That's it, nothing more. But it has to be reliable data or you lose operations confidence. And when you lose operations confidence, that's a bad thing. That's a really bad thing. I've had the opportunity to see a lot of different locations and how different end users implement their systems. And one of the things that stands out is we lack teaching the people that touch the metal, our resources, things about data. And this is extremely significant because data is what drives pretty much everything that we deal with. We talk about reliability from a perspective that we need to have reliable numbers because at the end of the day, operations and management really doesn't know what you touch in the field to get a value coming into the operations. They don't know. They wouldn't be able to point it out in a room full of analyzers. And so the reality of it is the people that touch the metal have a very unique perspective on what it takes to make the data happen. And reliability is absolutely a cornerstone. If we look at the American Society of Quality, we find out that there's 5 elements that tie into reliability. And this is really kind of significant. This is just a definition. And this is done by people that don't do anything except define quality. And when we talk about that, we need to listen to what they're saying and put it into our practice. In your site's practice, it's extremely significant to understand what it is you're peddling because you're peddling more than just numbers. You're peddling reliability, and if you don't maintain reliability in online time and that kind of a thing, sooner or later you start seeing lack of funding show up. As we talk about reliability, there is a significant need for data. And data comes in a number of different ways, but what we have to really understand is what are the elements of a data for it to have value. Here, I'm showing you that data value has to be timely. It means it has to be current to whatever that process is. It needs to be accurate. It needs to represent what that value is that operations needs, because operations, take it or leave it, is your customer. It needs to be reliable. Here's that reliability thing. Reliable. It needs to be online, always. Okay? When we talk about that and we say, well, what is your target for online time? Have you ever heard anyone say 50%? I want to get you 50% of the time, get you a good number. Right? It just doesn't happen. They want it 100% of the time. Is that achievable? Maybe, maybe not. It just really depends. The last thing is the data that you have has to be actionable. It means that there's such a thing as collecting too much data. That's a really big problem. Too much data does this for you. It confuses the issue. Too much data means you really don't know what you're measuring. Too much data means your design isn't around what is critical. So be aware that there is such a thing as too much data. There's two types of data, really. There's what I call as acute. I've talked about that before, but in reality, acute is something that happens right now in the real time. It's something that you can't really plan for. Something broke. Something went haywire. Something failed, an immediate fail. Now, what caused that immediate fail could be a number of things. Could be the number of actuations you exceeded some lifetime and you really didn't plan a maintenance thing around a valve breaking or a solenoid going out. It could be that you had a lightning strike on the other side of the plant. You blew a board in your analyzer. It could be that somebody on a forklift ran into a junction box. It could be just any number of things when you talk about what happens immediately. It could be that operations changed a ratio somewhere and all of a sudden sent a bunch of crud and it plugged up your filter. That's an immediate action. That's not something that you can actually plan for. It's going to be that way. It's not what you can plan for. What you can plan for is the things that happen over time, the things that are chronic in developing. It takes a long time to develop. If I'm going to have a valve fail, I may know that, hey, I get so many actuations out of this valve and I got to rebuild it, so count the actuations. It may be that I know as long as the process is running under this condition, I need to change a filter every 1,247 hours, whatever the number is. These are things that are predictable, things that are failure, things that can fail where you can actually measure the rate of failure. But to measure the rate of failure, you do have to have a frequency of data that makes sense. There's probably, as many people say, why do we want to validate an analyzer and what is that frequency that should be? And that's kind of a really good discussion to have, and I want you to think about that and discuss that if you will. Just think about it from your perspective, what your site is, what your maintenance strategy might be. What is a validation frequency? Sometimes it's daily, especially in the terms of environmental regulations, site permits. You get a 24-hour operating period, and if you fail a validation, the previous 24 hours gets chunked out. That's also something that you can apply in some cases, maybe not all, and to some cases, apply that to your process. Does it make sense to throw bad values into the process mix? Because when you do validations, it's really only an assumption that, hey, at this point in time, I've got a good validation. At this point in time, I've got a good validation. It's an assumption that what happens between those two validation points is good data. It's a valid assumption. It just means that we have 2 points in time where we know we challenged that measurement and the measurement worked. That's it. That's just 2 points in time. What should your maintenance be, and what should the length of that time be? Quite frankly, you need to set that to whatever your manpower requirements are, the technology is, because it makes a difference on the technology as to whether or not you need to validate technology or monitor the things that drive that technology. Right? What we're looking for is basically change. And we're looking for change in one of two ways. We measure change in the quality of the analytical itself. I might be looking at something like a bias signal or a current that goes to a detector, or a percent transmittance. Doesn't really matter what it is, a baseline offset. It doesn't really matter what that is. That's part of the technology. But we can also look at things like, what is the pressure differential across a filter? Or what is the flow rate change in a filter? Or what is the response of a valve changing to the flow changing? Right? I mean, if I've got a flow meter that's measuring some frequency, and I put a stop on a valve, I'm expecting that flow to stop. Well, what if you put that stop and you're notice that, hey, my flow doesn't go down now for 2 seconds or 5 seconds or 7 seconds. That should tell you that, hey, my valve's not operating. But you got to have data to follow that up. And this is kind of the neat thing when we talk about data. Data comes in a couple of different ways. And these are all aspects of things that contribute to the value of data or the quality of data. Timely, reliability, probability, availability, all those abilities. There's a bunch of those. But in reality, all of these impact whether or not the data you have is valid. And it's very important that your data be what you need to have, and that it be accurate, that it be timely, that it be actionable. You also need to know what is the frequency of update of that data. In older technology, about the only thing you have to do with older technology is run validations. It doesn't necessarily have all of the senses and sensors that we put into analyzers today. You just have to be able to check and look at what's going on or how it's been performing. Why? Because that's the way they were built. Has nothing to do with what was available today. It has to do what was available then. And believe me, if it's still out there running, management's probably not going to spend money to replace it because they don't see that as a problem. And that's a really big problem because that's a risk to that operation. How many of you have gone to management and say, I need to replace this analyzer, and they tell you why it's still working? That sound familiar? No money. That's what happens, no money. Until it's a problem, it's no money. Why do you think that's happening like that? I would submit that one of those reasons is that you're not getting the information that needs to be delivered to management. Maybe you don't have the tools or the reporting format, but that is really a big problem, is that management has to have the information to make decisions on, because quite frankly, an analyzer is nothing more than a widget they spend money on that they expect a return of value on. And if you're not giving them a report that says what that's going on, what that value coming back is, they have nothing to base a future decision on. Does that make sense? They have to have it. Why? Because they're not out there changing filters. They're not out there clearing lines. They're not out there working on stuff. But they have to know you're out there doing it. And they need to know when you're out there doing it what effect that has to the reliability and online time. Your job, though, is really to reduce that. We want to get the plant data. You want to have high availability. You want it to have high trust. But in order to do that, you have to have a maintenance strategy and a maintenance work schedule that supports that technology. Now, notice I didn't say in general that technology. What does that actually mean? That means depending on what it is, you're going to have a different frequency of inspection depending on the technology, the stream, the things that go on. And some of you have some really simple applications. You may think they're really fantastically simple or they're difficult, but there are then others of you that have some serious issues. You have some really interesting applications, and they're booger bears, quite frankly. And so the reality of it is you want to have high value from management in the data you're giving them, but you're going to have to let them know what's going on and what the condition is from where that data is coming and what the condition of that equipment is. So we just don't know everything, and neither does management. And that's why I push that so hard, and it really may sound kind of crazy about that, but quite frankly, management's the people who decide where the money's going to be spent. That's it. That's it. And generally, it's not significant to them until they don't have it anymore. Until they don't have it. The problem we have, though, is what happens if your data varies? Can you trust the data that you're giving to management? That's where the observation is that we don't necessarily teach the language of variation, or that we teach statistics and that type of thing to our groups and resources that touch the metal. And that's one of the reasons why we want to talk about variation of data just a little bit today. Because as we look at data, a histogram, sigma, that type of thing, I feel like I'm preaching to the choir here. My apologies. I know this is probably basic for a lot of you. But the reality is this has a basis in fact on statistics. It's a very well-known application, and we need to understand how that variation applies to the things that we can use at the analyzer level to make sure that we're running the things that we want to see and do. I think our biggest information comes from just basic statistics, our standard deviation formulas and things like that. And that's kind of really significant to know that it happens. But we don't really want our resources out there calculating that stuff. It just needs to be collected so they can evaluate the patterns. The pattern recognitions of data is very, very significant. In fact, when we look at this kind of a thing, and we look at what we call as can be good or what is possible, this type of spread of data applies to pretty much every analyzer we throw out there. And it applies in ways that we may not think about it. We look at things really and truly, we talk about things like CP values. How many of us really know what a CP is in statistics? What does CP mean? Raise your hand. You see this little chart right here? Let's see if I can get this thing here to work for me. No, of course it's not. That little hump of data, that histogram and then that represented chart, if we were going to put those two red lines together, the distribution of data between those two red lines and the ratio to what the chart is, it becomes what your CP is. It is a ratio of the width of your data to the width of your spec limits, basically. That's all it is. And a CP of 1 means your data is a perfect fit. It means that from red line to red line, 100% of your stuff comes in, and that's fantastically well. But as we look at that, this is an overall great statistic. But one that we move a little bit further down into is something called CPK. CPK is the value that you really want to achieve. And statistically, a value of, I think, 1.33257, but who keeps up with the detail? But 1.3 is basically what we call, we're in control. That's the perfect, we don't need to be any better than that. When you do this ratio of CP versus CPK, the difference is this. If this hump of data would slide up above these lines, your CPK value is going to drop like a rock, okay? Because what it's telling you is that your data is not centered between your two specification limits. You may have a good spread of data, but it's not centered on where it needs to be centered, okay? As you get better information, let's say that little hump, it gets really thin, narrow, and tall, but it stays centered. What happens to CPK? It climbs like crazy, huge number. But here's the trick. Here's the really significant thing. This is a value that you can keep on a running tab. This is something that you can look at and you can decide whether or not you have an issue with your data. An issue with your data is an issue with the way your data is delivered. That's your sample system, your sample handling system, your analyzer. It could even be your technology. It's possible that you can perform a measurement with technology that's really not the proper technology for that. It's going to show up on a CPK because a CPK takes everything into consideration, the spread of data, how well centered it is on the thing, the shape of that curve. It's huge. And when we say 1.3, we're saying you get a 1.3, you're great. Anything below 1.3, you need to look at something. Something's not going right. If you get greater than 1.3 and way greater than 1.3, it might mean you're putting too much maintenance into that system to keep it there. So as we look at these things, what we're going to talk about, just to show you some examples of what we can do or talk about this, is what is in control and capable. When we talk about being in control and capable, we're really talking about a trend of data that sits between specification limits and it has a CPK of 1.3 or greater. And this isn't your process measurement. This is you challenging that technology with something that you know what is, the value of, and you're doing the ratio of how well are we recovering that. So if we say I've got material A that has 100 ppm and I measure it and it's got 97, 98, 102, 103, and it bounces back and forth like that, that's a pretty good number. But if I've got something I've got 100 ppm and it reads 85, 115, you got a problem. You got a problem. So your CP is going to be bad, your CPK is going to be bad, and that becomes kind of an issue. As we start looking at these, what's in control and what's capable, this is really where we're talking about control charts. And this is really where we talk about run lines too. We can look at data more than just did I violate a line. We have a number of run rules. And this is an example of a few of them where you get so many above a median or in a certain direction or below or a cycle. I guess the most significant control chart that you can see is that non-random pattern cycle, because that looks like, hey, it ought to be in control. But you need to look at the medium. You need to look if it's cyclic. And it's a big thing. When we look at this kind of a deal and we see this information showing up, none of these patterns tells me that you have this system in control. This is a bad performing system. So this is going to be some real world data we're going to come across in a minute, and I'll share that with you, but we're going to talk about control versus capability. As we look at this information and you look at a histogram and these curves that you get, the reality is you have special causes that can slide these groups of data apart. Now, what do those little hills represent up there? These represent points in time where we ran a series of validations. That series of validations is represented in one of those little hill shapes. And as we look at that, you can see they're shaped differently. Some are more narrow, some are taller, some are wide, some miss the center line, some go above the control limit, they're outside the control limit. All of these are patterns that show different things that you can see in a control chart. They all basically mean we've got a problem, okay? Now, the one up here, as we start looking at that, what we're really looking for is what happens and what kind of CPK would these representations show? And I've given you some kind of examples up here, okay? And the only one that really looks fairly decent is going to be that one in the top left-hand corner, and it's really not all that good. But the rest of them, where they look like they could be here, they're all problems. And the reality is, you need to look at that from a maintenance perspective, and you look at it from a maintenance perspective in terms of something that's chronic, not something that's acute. These things don't happen because you got a filter plugged. These things don't happen because something broke. These things happen simply because their spreaded data over a long period of time is now indicating the CPK value of something less than 1.3. And that's something that you can kind of garner with. And as we look at these things, you can kind of look at those. Those are kind of hard to see, it might be up there, but you can basically see where you can, if you have a system in control, your control limits can be narrowed down quite well. And if you narrow them down and you get a problem that pops up later, you've had something that changed. This is real world, by the way. This is the information that we have has been whitewashed, and it was provided by one of the chemical plants. And so everything that we're going to show you in this is actual real world examples. Here's some histograms. And this is what I'd like you to see, is when you look at the histograms, or the little groupings of data, of how you want to look at that, you can then see what some of these CP and CPKs are. And if you can see what we're looking at, the little red numbers and the yellow numbers, these are numbers that pop up that explain to whoever's looking at it that you got a problem. But you got to look at the data. You got to look at it. So when we talk about performance or looking at data, it really falls into two categories. One is performance monitoring, one is diagnostics monitoring. What is performance monitoring? Performance monitoring is basically your validation frequency, whatever that might be. And you look at this kind of a thing and it represents past performance. It has nothing to do with what's going on right now. Diagnostics monitoring can be continuous or discontinuous. Continuous, and I guess the definition difference between continuous and discontinuous is that continuous is on a regular basis, and ongoing. Discontinuous is maybe not on a regular basis, but it's ongoing, so I don't know that there's really a difference there. But this is something that you would do, trend like the technology. I'm looking at things like a bias voltage. I'm looking at transmittance. I'm looking at things that reflect the technology that you selected for that measurement. You know, there's a lot of ways. When we start getting into this diagnostics monitoring, we're going to end up where you can actually start doing predictive failures. And that's kind of a big way. You can do predictive failures with performance monitoring as well. But as we go through these, and we talk about some of these cases I'm going to show shortly here, is it goes to, you can monitor by validations or you can monitor by technology, doesn't really matter. It matters that you have someone who looks at the data and understands what they're looking at. You need control charts for that. Otherwise, you have them going. The last thing, I guess, really is what is the validation frequency that you really want to have? Oh, I just got a high five. I've got to hurry. And so this is something that's a site-specific issue. That's a site-specific. You're going to have someone at your site that's going to be responsible for this. Let them pick that. They know the technology. They know what they can do. This is really something that needs to happen at the site level. And it needs to be done by people that are experienced with the technology and the process. At the end of the day, here's a few examples. Here's an example of where someone's maintenance strategy actually calibrated out the fault. This was a detector that read 10% the value of the real value as it was first delivered, and they did a monthly calibration. As the change happened in the technology, they calibrated to that change, and so as a result, they lost the ability to do any kind of diagnostic information on it. They really had a 7 to 8 month window. Here's another example of a slow fail where they're doing calibrations. Each one of these little calibrations that you're seeing, those little segments, those become very significant. If you look at the slope of the segments between the first and the last, if you're looking at those systems really and truly, what you can see is as that slope changes, the frequency of the fail happens a lot better. Here's an analyzer that goes out of control. Slow fail with an external influence. This was actually a diaphragm pump that had a hole in it. And so it's something that affected that system. But the benefit here is look where they caught it. They had a 2-week failure period here, but here's what happened. They caught that before it went out, so operations never really got a bad number. They always had a number that was in control. Here you can have run rule violations, easy to see. And so what does that translate to in operations? It translates into confidence. The ability for operations, if they have belief in the value of the data you're giving them, lets them run closer to the control point. This is a real world example. Look at the two different lines. See the little purple line versus the dark blue line? After they corrected the issue and started really doing some overlays with it, look what that allowed operations to do. Operations closed their run point significantly. What does that translate into for your company? Production increase, margin, all of the above. It's good things. And when you put this kind of information in front of your management and you say, hey, I need some money, the probability that they're going to agree with you is fairly significant. In this case, this is one of those things that perhaps doesn't happen everywhere, but it's absolutely one of those areas that this is an excellent opportunity of when you have data available to analyze and you apply that data to your maintenance situation, the reliability can go way up. The confidence in those values can go up. But in order to do that, you do need to have a data system that collects that for you. You need to have something that looks at it for you. And you need to teach your first line resources how to look at data. That's just really huge. And it's a vicious circle. As we look at these systems, what we're really talking about is as the reliability in analyzers goes up, the confidence goes up, the ability to run closer to production lines, to design, happens. It happens. We actually back in the day when we did some of this across a unit, we actually got to re-rate an operation just simply because we had analyzers that could run to the control point. And so what does that mean? They were running within 1 to 2 parts per million of their target. That's how good, that's the value that they gave to them. So this is something that you can do. What I'm really talking about is that, hey, we need data to actually make decisions about 2 things. 1, your maintenance. What is your maintenance schedule should be? How you should respond. And 2, how you can present this information to management to maintain your funding. It's really a good thing. I would like to recognize that this information, most of this information came from Dow. Dow's Siemens partners with a whole lot of companies, and this is one of the systems where they have it. Chris McGarvey provided this with the approval from Dow. And then we also have, oh, never mind about him. And so that's kind of where we are. That's it. I want to say thank you for taking time to listen to me today. Yeah. Swing by the booth. We have it right there. Change the way we train our folks at the level that we train them. Looking at data is significant to maintaining reliability and accuracy of your analyzers. But yeah, come on by the booth. I'll show you everything we got. We got an active system there. Thank you.
Thank you, Michael. Let's see, let me bring up your bio real quick.
Sure that's out. Yeah. Okay.
Just have you introduce yourself. All right. Our final speaker of the day and in this session is HP Visser with ASAP Products. I'm going to let HP introduce himself here real quick. And thank you for participating and for your paper.
Thank you. Okay, thank you very much for being here. It's the last session, the hardest session. But okay, I'd like to thank you. Thank you for the introduction. First of all, I'd like to thank 2 people. Actually, Dirk Horst, he's a former NAM and Shell employee. He was a QMI consultant for his entire career. He's now a freelance trainer. And my colleague, Martin van Burg, he's currently our CTO. He developed and created a program what the previous speaker was talking about, how to collect data and interpret it. Martin is manage our R&D facility as well. They both are a sounding board for the youngsters within our company. Speaking highly about them, they create also a problem for me because it is their presentation, their experience, and not mine. And what do you think about the titles? Hey, 4 o'clock in the afternoon, eh? I'm the last speaker. Let's face it, it's not the most exciting title you can have. But like a previous speaker said, it is one of the most important subjects in our industry because it determines if the analyzer is working properly, yes or no. My presentation is of the paper is about a software tool, what you can do with it. And actually, I want to challenge the audience a little bit to think into the future. So I'm not going too deep in what it does, but what it can do for you in the future. It leads me to a real situation. If we approach end users with a package like such, and we say, well, it can save you so much time, so much money, you get all the data, but the main problem is they don't have time. So you're catching up in a catch-22. It's the same with students. They need experience, but without work, you don't have experience. So my aim for today is to combine these two groups and actually to gain from a curse of a blessing. Everybody with children in the audience know exactly what I mean with this picture. We say to our children, why don't you go outside and play, be playful, go outside. So finally they do. They go outside, they play with their friends, and they're still watching on the telephone. Meanwhile, we adults, we are doing the same, by the way. But we have a Dutch guy, Bertolt Gunster, and he introduced flip thinking. And flip thinking means something like, if it appears to be a disadvantage, why don't you turn it into an advantage for yourself? So, what should be a relatively boring subject, I thought to myself, well, hey, no guts, no glory. I'm going to do something extraordinary. So first of all, I would like to ask, are there any teachers or students in the audience? Would you raise your hands, please? Can you keep them for a while? Are there any end users in the audience? Can you raise your hands as well? Can you look to each other? Because from one group, I'm going to connect one of them. Thank you. You can lower your hands. What I'm going to do, I'm going to connect you and I'm going to challenge you. So the first giveaway is to the end user. For that end user who can write me a motivation why he should get our system for free, and it don't have to be a prosa, just bullet points. He will get it for free, including support, including my Houston-based colleague, including my Dutch-based colleagues as well. But there is a but. This always comes with a price. He or she must be committed to use it and to spend time in it. They also must be committed to help the students, that particular student we are choosing, to help and guide them. And the last one is a request to stand next year or the year after here and present the lessons learned and present what it brings to them, what the real value is. Okay, now to the students. The one we are selecting, we're gonna give you a theoretical training, we give you a hands-on training. We are not going to do it via Teams. We're going to do it in Amsterdam. So we will buy your ticket, we will pay for your staying, and if you work your butt off, we probably will teach you how to party as well in Amsterdam. So, at least I hope I have the attention of 3 groups. You might 3? Yeah, the end user, the students, and my competitors. So I was glad that the previous speaker was explaining all the details or all the things where it is going about in perfect detail. So I will go quickly over it because I want to go to the real challenge. But some basic definitions, we look at accuracy in terms of uncertainty. We look at precision in terms of repeatability. In practices, we have either a gas chromatograph or any other analyzers, and we expose it to an external reference. Typically, it's known as a calibration gas, but it can be also a lab sample. There are various ways to do that. That is what we're going to teach you how to apply it. That is actually the basic of the system. Yeah? So why do we validate? To determine the accuracy, to determine the reproducibility rate, and actually to provide the proof. We go a step further is, like Michael said in the previous discussion, is it's something plant specific. I slightly disagree with him. It's an ongoing thing what you learning the analyzer. So we go by step by step. So actually I want to discuss some practical examples, what we have achieved, and actually I want to challenge the group, what you discover, what it can do. So typically we not only want to look at the analyzer, but we want to look over the whole system. Because if the system fails, your analyzer fails, and it can have a perfect validation, but still the value is not good enough. So typically, this is what I get of one of our end users in the Netherlands, which are using our system, is this is how they start their working day. And they have a clear overview of all the software for all the analyzers, and they immediately go to the package. I hope I don't have to explain the meaning of green, orange, and red. What we all can see will be an easy day. Yeah, there's only some checking to be done. And you can go up to plant level, unit level, analyzer level, whatever you want. But we try to pull more and more data from the systems. Actually, what we try to do is, before you go out in the field, that you have a glimpse of what is going on inside. So assume that there is an error or whatsoever in the field. If you know already a direction where to look at or to think at, you can start processing already. So you can do it in the car or on the bike, what we do in the Netherlands, and you start thinking, well, what could be the root cause? But also taking parts with you. Instead of going to the analyzer, pressing all kind of buttons, and see what the symptoms will be. So that can be very helpful. That's at least what we try to give. Another practical example of a gas chromatograph with a liquid injection valve. And according to the manufacturer of this valve or this GC, is every quarter the valve should be maintained, meaning replacing the seals. And this end user had the feeling, well, maybe we can extend the interval a little bit. So what we did is once every week, we have had a couple of blank injections, so just a carrier gas, no sample. So what we're looking at, do we see any sample on the detector if you're running a blank? So that means that there is a leak. So what you can see here on the arrows on the left-hand side, that should be the first interval of replacing the seals. Nothing happened. Then we went to the second one. And there we start seeing some movement, and it's minor, it's 0.1 millivolt. So it can be noise of the detector. But what you see afterwards is interesting. There you clearly can see that a leak starts to occur. And it is still 2.2 millivolt. It's far below the threshold which we put of 5 millivolt. But at least you can start planning to do preventive maintenance instead of ad hoc, because that's always on Saturday evening or on any other inconvenient time. So you can imagine there are all kinds of things that you can monitor on the system. Like Michael was saying, you can look on valves. Some of the valves, they have 1 million cycles, so you can put a timer on it, and at 970, you can plan a preventive maintenance program. The one who knows me a little bit, they know LNG is my middle name. It's a sort of hobby. And we're doing a lot over there. We're building vaporizers, samplers, but we're using this system also to monitoring the whole process. It's a batch process. It's a batch process where a lot of money is involved. To give you an idea, the Netherlands were buying a couple of cargoes last year, and the average value was $300 million US. I don't know what you make per year, but for me it's a lot of money. But also the amount of uncertainty is also a lot of money associated to it. So we clearly want to monitoring the whole loading or unloading process. So it starts with the validation. Like Michael already explained, it's a validation and we monitor that. But we have so much more power into the system. For instance, there is a gas chromatograph, so we're measuring the composition. We know the pressure, we know the temperature, so we can draw the phase envelope of that particular sample. LNG is a cryogenic liquid, a very nice phase envelope, as you can see in the middle picture. Once we know the pressure and the temperature, we know exactly where we are sampling from the process line, because the standard says you should be in subcooled conditions. What does that mean? It doesn't give any value, it's just an empty phrase, because you're running blind. Now with this tool, you're not blind anymore. Actually, you can determine the degree of subcooling. Going one step further, if we're monitoring, for instance, the calorific value continuously, we're looking at the moving average. But we're looking also on the moving average of the uncertainty. And from that data, we can see if something goes well or not. And with this kind of values and within the limits, hey, everything is fine, everything is under control. Excuse me. Why is that so important? Because it's a very helpful tool. And this is a real example we experienced 2 months ago. There was a floating facility we were starting up. And that means they cooled down the whole installation. So they were making LNG on the top sides, then into the big vessel, they degas it, and then there was a 30-inch downcomer in a line, horizontal part, and there was our vaporizer, and then go to the tank. Get a call, phaser is not working. I've heard it before. So I'm not getting excited anymore in the sense of panicking. Just look at look what is going on. And we immediately saw it already what was going on because they were sampling from the dual phase. But this tool gave so much insight to this customer as well. So we asked, can you get a process engineer involved and pull the P&ID? And they did. And it's always funny. You make the assumption that I've a line from the top, I have a horizontal line, so it must be filled. But they were cooling down. So these huge tanks, they were spraying from the top. So there was no pressure in the pipeline. And actually, there was a lot of gasification already in the pipeline. And it is funny by teams. If you look to the process guy and he's looking, oh, with the F word, and he knows exactly what was going on. Then you know what the root cause is and you can take some steps. So actually in a process where you can't look into because it's heavy insulated, with this gives a lot of information. In Amsterdam we do a lot of exciting things. We're drilling holes in vaporizers, we put in a cryogenic camera and we can look into it. We can't do that in the real world. Sometimes I wish we could, but we can't. But based on data, on what we distillate from our system, we can see what is going on. So, bring us to the next challenge. And I heard it a lot, and therefore I'm very glad that the students are also here. Like I said, we are very connected to LNG industry. And if you see in Louisiana only what they are doing in terms of LNG, and if you look at the local population, 5,000 people, more than 4,000 are working, they're creating 11,000 or 1,100 jobs. So they're coming not from local, despite the 23,000 people which are needed to build the plant. So it is an issue. So what we try to do with the system is to create a tool for maintenance and to help, to focus on the things which are really necessary and the easy things that we can skip that. And therefore we need the youngsters, because their affinity with the screen is much better than the gray hairs here in the audience. So I'm challenging you. So to conclude, so everybody who wants to deal with the contest, write us an email to info@asa.nl in the subject line ATC 2023 AIM, and just, I don't need prosa. Just send why you should be the guy, girl, or end user, whatever, to hook up with us, and within a month we'll let you know who won the contest, and hopefully you are presenting next year here instead of me. Then we can look then we can hear proper English and not the brown coal English from a Dutch guy. So I'd like to thank you very much for your attention. If there are any questions, I will be delighted to answer them now or later.
Any questions? Any questions from the students? When does the flight leave to Amsterdam? If we've got no questions, I would like to remind everybody to get your paper scores to this gentleman up here. And with that, we'll wrap up the first day. The exhibit hall is open tonight, 5 to 7, for open bar and food. And we hope to see you down there.